Okay, hello everyone and welcome back to your YouTube channel and welcome to this very exciting and practical video of today. As you must be aware, I am working in this master level course about advanced power systems, and one of the very important topics there is frequency control and frequency stability. So in the previous video, I told you about the system frequency response model, and specifically I explained the concept that was introduced by Paul Anderson in 1990 in his very brilliant paper, Low Order System Frequency Response Model. And in that video, I explained to you that when you are interested on the frequency response in traditional power systems, I mean, based only in synchronous generators, so you can use those linearized low order models. So today, the video is extremely practical, because what we want to do is to show you how to implement one of those system frequency response models inside one modeling and simulation software. Specifically today, we are working with a single area control area power system without any frequency control. So the idea today is that we are planning to implement this low order system frequency response model. And I believe you must remember from the previous video that I say to you that this model is quite exciting, because in this model you have the representation. You can see over here you have the representation of the system inertia. So you can see H, that is the rotational inertia constant in the system. But also on the left hand side here we have the frequency dependent of the whole loads. And on the top, you can see this is the frequency dependence for the static loads. We are using this gain over here, the L, to define how the active power change when there is a frequency deviation. And the L is a constant that is defined by hertz per megawatt in terms of units. No. Here, this is a very exciting representation. We have a derivative term. That is the reason for this letter S here. And you can see that we have a gain to W0, F0, okay? So what we are planning to do is create this block diagram inside a simulation software. In this case today, we are dealing with Simulink. We are using Simulink because it's the very simple and the most easy way for people that is introducing themselves inside the simulation wall. So we are using Simulink. However, you must be aware that also Simulink will allow us to create those models, and it will be used for real-time simulations using OPAL-RT. But also, if you go to the GitHub repository in a few months, you will have also the system frequency response model coming from Typhoon Hill. So without further delay, let's go and let's start to create this model of power system without frequency control inside MATLAB Simulink. So here we are here inside MATLAB. This is the classical environment for MATLAB. You must identify that here at the top we have the toolbar, and there is an icon over there to start Simulink. So what I suggest is that you start Simulink and create an empty model. Depending of the performance of your computer, that can take some time depending of the specification of your hardware, okay? So here we are. I already create this empty Simulink model, And this is the model that we will be using to create the model of the power system without frequency control. So let's start with the following. Let's put here a gain. We need a gain, and this gain will be used to represent the model. Remember, 1 divided by the L, and the L is the frequency dependence, of the load, okay? As you must be aware, I am using letters over here. Because I want to configure this model in order that you can replicate several simulations. And let me change the name here. This is frequency dependent loads, okay? Also, I would like to include the model of the rotating mass loads. So let me use another gain, and this gain will be a bit more complicated because the numerator will be 2W0 and the denominator will be F0. So let's apply that, and we have now the model for the gain, and this gain will be rotating mass. Let me put over here rotating mass loads, okay? Also, we need a derivative term. Let me use here a derivative. So we are using here a derivative term. So now we have the rotating mass, okay? I also need a zoom point. And in this case, I want the zoom point to be with in this way. Let me put like this. Perfect. And now the active power deviation, coming from the static load and also coming from the rotating mass, they will be out up, and then we will go here. Let me put another zoom. Yes. And now what I will do is I will rotate this, format, rotate. Let me probably change like this. Let me go here and change the list of signs. So let's see. Right now we have in the proper direction, because from here, from this adding point, we are going to the next one. And remember, this is delta P load F, because this is the change on the frequency deviation, okay? The input will be a step, because we are planning to use a sudden increase on the load. So we are using here a step. It will happen in t equal 1. Initial value is 0. Final value will be P load, okay? dP load. And that is going into this adding point, okay? So now, something that I want to do here is include a manual switch, because I want to show you that that rotating load, has some impact on the simulation. So let me put like this. This is a switch that you can change the location just by double clicking on the symbol, okay? So when the switch is up, that means that there is no rotating mass load. When I put the switch down, that is rotating mass load, okay? So again, I need another adding point, another zoom point. And in this case, I need this one to be like this. Let's see. Because this is coming from the loads. And this is the delta electrical power. This is the total electrical power. And here we have the power demand change. So something that we need to remember is that the electrical power is negative. Remember the swing equation. So right now we have in the proper way. So I need now a transfer function to represent what's supposed to be the system inertia. Remember, the numerator of this is F0. We apply over there F0, and the denominator should be like this. Let me put here a 0, and twice h multiplied by h base. So now we have here a transfer function, and this transfer function, beautiful transfer function over there, is representing what we call, in this case, we call this the system inertia. Now we have the output here, and the input of this block is the acceleration. This is the acceleration power deviation, and the output is the very important frequency deviation. So we can call here df, okay? Let me put the name of this signal. It's very important. This is df, because this is the frequency deviation, okay? Another thing that we need over here is a constant, and this constant will be representing the mechanical power deviation, and I will go here positive, and in this case the mechanical power deviation is 0. Let me put here the name. This is delta mechanical power, and this signal over here will be. So right now we have completed the single line diagram, the block diagram here. So probably what we want to do right now is, if we try to run this model, we will have a problem. And the reason for this problem is because those constants over here, F0, H, and so on, they are not defined. So to define the constants, what we need to do is go in here to modeling, then go here into model, and then we will go here into callbacks, okay? So here in callbacks, I am including the frequency, 50 Hertz. I am including here the rotational inertia constant, and in this case, the rotational inertia is 5. We have here the base power, that is 1000. We have here the definition for the frequency dependence of the load. In this case is evaluated, that is F0 divided by the base power. We have W0, that is 100, and we have the power deviation, okay? So now we define the initial value for every single parameter. So we are almost ready for a simulation. So as we are ready for simulation, let's check here. In this case, we don't need to change many things here. We are keeping variable speeds, automatic selection for the solver. So let's run the 30-second simulation over here. Yes, and the simulation is done. However, we are not presenting any plot, and we don't have any error. That is the good news. So what we need to do is define a scope. So in this scope, what I will do is creating the plots. Yes. So in this case, we want to plot how many variables? We want to plot here the payload, the acceleration, the mechanical, and the frequency. We are talking about 4 variables. So double click at the scope, select here settings. We are selecting 4 inputs, and it will be one on the top of the other. So right now you can see that I configure my, my scope to show 4 time domain simulation variables. One will be the power load. One will be the mechanical power. Another one will be here, the acceleration power. And finally, we are including here the frequency deviation. Something that I will do also is to include here a digital display, here, and let's do that. Sorry, I make a mistake, is display. display. So let's include here the numerical display. So right now we can run the simulation. And as you can see, we have a frequency deviation, in this case, after 30 seconds. We have a frequency deviation of minus 4.752 hertz, okay? Let me run again the simulation. And here we have the amazing plot. And let's see what is happening here. What is happening here is very simple. The first plot at the top is the load change. You can see how the power deviation at the load is moving from 0 to 100 megawatts. There is no mechanical power change. It's 0. It's keep constant. And here you can see the acceleration power. The acceleration power will be the difference between the electrical power and the mechanical power. However, what is important to see, let me include one more plot over here. Let me include 5 plots. So right now we have 5 inputs, and let me organize this. Yes, we want the 5, 1, 2, 3, 4, 5. So now what I will do is reconnect the signals over here. I will include the signals in different order. Let me check this because I want my students to see the proper effect here. So we have here the change of the frequency coming from the load. We have the acceleration power over here. The mechanical power. We need to include the mechanical power here. And then the acceleration power. And finally, we want to show the frequency deviation. Okay, let me include the names on the plots. So now we will be able to see. Let me run the simulation. And now you can see what I am talking about. We have an increment here, a step going from 0 to 100. You can see how the frequency dependence of the load is making this one is making to go down the active power consumption of the load. Here you can see the mechanical power deviation, and here you can see the active power acceleration. And finally, what is very, very important to see over here is the frequency. And as you can see, the frequency is going down, and I can assure you that this frequency, let's run 300 seconds. And you can see how the frequency is going down. The frequency is going down and reaching a steady state. In this case, the steady state is in minus 5 hertz, okay? However, what is important is, let's see what is happening if we include the behavior of the rotational load. So now what I will do is, now I am running again the simulation. But in this case, I include the effect of the active power consumption when we have the rotating mass. If you look the numbers in a steady state, there is no change. There is no change in the steady state frequency, something that we clearly see that is happening, because in a steady state, this derivative term disappears, is not doing anything. However, this term is modifying the frequency, the rate of frequency change suddenly after the load change. So I will not spend more time here. I can make many explanations. However, this was a very simple, a very basic video to show my students how to create the model. In the coming videos, I will tell you how to use those models for analyzing the frequency response behavior. But at this moment, I am really happy that I introduced you to the amazing work of MATLAB Simulink. And right now you are able to create the system frequency response models that you need to do. Well, this is the end of this video. Thank you very much for watching, and I will see you at the next one. Bye now.